let's start with a square with a side length of 6, and then let's construct another two squares with a side length of 2 so that they are located at the bottom right corner of our bigger square, just as shown in the sketch. Now let's mark the upper left corner of our bigger square as A, the down left corner of our small square as B, and the down right corner of the other small square as C. Now, is it possible for us to find the area of this red shaded triangle ABC? Since there are numerous solutions to this problem, I would advise you that if you want to try this problem for yourself, you do it at least 2 different ways. So, if you want to do that, now is a great time to pause the video and then come back to see the solution. Alright, let's get to the solution. So, as I mentioned earlier, there are numerous ways to solve this problem. For this video, I will show you 5 different methods to solve this particular problem. Alright, let's get to the method number 1, the difference of the areas. So for this method, we will first set the boundaries around our sketch, and we will try to find the measurements of this yellow rectangle. First, you can probably notice that the length of this yellow rectangle consists of lengths of our two squares, our bigger square with a side 6 and our smaller square with a side 2. So that means that the overall length of this yellow rectangle is equal to 8. The same applies for its height. Since it consists of the heights of our two squares, that means that the overall height is also equal to 8, so of course this means that this yellow rectangle is actually a square. Now let's find the other measurements that we need. First, you can notice that our yellow square contains the red triangle, but it also contains 3 right triangles. First will be this blue triangle, which has the length of 8, and the height will be equal to the length of the bigger square, so that is 6. Now you can see the green right triangle with a height of 8, and the base must be equal to the side of our big yellow square 8 minus 2 sides of our smaller square with a value of 2, and that means that the base of this green triangle must be equal to 4. And last but not the least, the purple right triangle with the height of 2 and the base of 2 times the side of our smaller square, so that is 2 plus 2, which is equal to 4. Now it's easy for us to find the area of this red triangle, since it is equal to the area of this big yellow square with a side of 8 minus the combined areas of our 3 right triangles. The blue right triangle with the base of 8 and height of 6, plus the green right triangle with the base of 4 and the height of 8, and plus this purple right triangle with the base 4 and the height of 2. Now, if we translate this diagram into formula, we will get the following. Now we can continue on by substituting our values. So the area of our yellow square is equal to 8 square minus the combined areas of our 3 right triangles. So in our case, for the blue triangle, that is 8 times 6 over 2, for the green triangle, that is 4 times 8 over 2, and for the purple triangle, that is 4 times 2 over 2. Now we can work through this and get the following. Now we can simplify this and get that the area is equal to 64 minus 44, and we will get that the area of our red triangle is equal to 20 squared units, and this is our solution. Alright, now let's try the method number 2, the method of using the right triangle. So since we already found certain measurements in the method number 1, we're just going to use those measurements in this method as well. So for this method, we're going to set our attention to this green right triangle and to this purple right triangle. If we isolate those two triangles, you can see that the green triangle has the height of 8 and a base of 4, and that purple triangle has the height of 4 and a base of 2. Now, can we somehow prove that these two triangles are similar to each other? Actually, we can, because we know that both of these triangles are right triangles. That means that both of them have the angle of 90 degrees. And we can also notice that their sides are proportional. If you can notice, the proportion between the heights of these two triangles is equal to the proportion of their bases, which is equal to 1/2. So that means that these two triangles must be similar triangles. And that means that they have the same angles, which we will mark as alpha and beta. You can notice that the value alpha plus beta must be equal to 90 degrees, since the sum of all angles inside the triangle is equal to 180 degrees and they are both right triangles. Now we can apply this knowledge to get the angle at the point B of our red triangle. Since that angle makes 180 degrees with angles alpha and beta, that means that the value of this angle must also be 90 degrees. Now we have the mathematical proof that our red triangle ABC is in fact the right triangle. So we will continue with finding its legs. We can first label the hypotenuse of the green triangle as A. But you can probably notice that that hypotenuse is equal to the leg AB of our red triangle. We can find the value of A by using the Pythagorean theorem, so A squared must be equal to 8 squared plus 4 squared, which is equal to 64 plus 16, and that means that A squared is equal to 80, which means that value of the side A is equal to square root of 80. Now we can do the same thing for our purple triangle. We can label its hypotenuse as B, and we will notice that it is equal to the leg BC of our red triangle. We can also find the value of B through Pythagorean theorem, so B squared is equal to 4 squared plus 2 squared. That means that B squared is equal to 16 plus 4, and that is equal to 20. So that means that the value of leg B is equal to square root of 20. Now we can use these two legs to find the area of this red triangle. Since we know that the area of any right triangle is equal to the product of its legs over 2, we can just substitute our values and we will get that that is square root of 80 times square root of 20 over 2. That means that area is equal to square root of 1600 over 2, which is equal to 40 over 2, and that means that the area is equal to 20 squared units, and again we have our solution. Now let's try the method number 3 using the Heron's formula. For this method we are going to label all sides of our red triangle as A, B and C. Now we can set our attention to this blue shaded right triangle with the hypotenuse A. We can easily find this hypotenuse by using the Pythagorean theorem. So A squared must be equal to 8 squared plus 4 squared, which is equal to 64 plus 16, and that is equal to 80. So that means that A is equal to square root of 80, and we can simplify this to get that A is equal to 4 square root of 5. Now we can set our attention to this other blue shaded right triangle with the hypotenuse B. We can find the hypotenuse in the same way, so B squared is equal to 4 squared plus 2 squared this time, which is equal to 16 plus 4, and that is equal to 20. So B must be equal to square root of 20, which we can simplify as 2 square root of 5. We will do this again for this new blue right triangle with the hypotenuse C, and we will repeat the same process. So C squared is equal to 8 squared plus 6 squared, which is equal to 64 plus 36, and that is equal to 100. So that means that C is equal to square root of 100, which means that C is equal to 10. Now we have all the sides of our red triangle, and now we can use the Heron's formula to get the area of this red triangle. The Heron formula states that the area of any triangle is equal to the square root of S times quantity of S minus A times quantity of S minus B times quantity of S minus C, where S represents the semi-perimeter of our triangle, so we can calculate it as the perimeter over 2. Now, if we substitute our values for A, B and C, we will get the following. We can, of course, simplify this, and if we divide both our terms with 2, we will get that S is equal to 3 square root of 5 plus 5. Now we can plug all our values back into the original Heron's formula, and we will get this huge equation. If we simplify things underneath the brackets, we will get the following equation. Now we can notice that the combination between the first and the fourth factor will lead us to the formula for the difference of squares. The same thing applies for the second and the third factor, so we can combine them to get the following formula. So now we can get everything squared and we will get the following. From here we will get that A is equal to square root of 20 times 20, which is equal to square root of 400, and that means that our red area is equal to 20 squared units, and again we have our solution. Now let's try the method number 4, the analytic geometry method. Again, at the beginning of this method we are going to save some measurements which we got earlier, then we are going to introduce the x and the y axis. Now let's try to find the coordinates for the points A, B and C. Let's start with the point A that has the coordinates of 0 and 8. Then let's notice that point B has the coordinates of 4 and 0, and the point C has the coordinates of 8 and 2. Now we will use the formula for the area of the triangle from the analytic geometry, which looks something like this. The area of any triangle is equal to 1 over 2 times the determinant, which contains the coordinates of all vertices of this triangle. The first column contains the x coordinates of our points, the second column y coordinates, and since this is a planar problem, our third column will contain only values of 1 since we do not have the z-axis. Now we can substitute our coordinates into this determinant and we will get the following. From here there are numerous ways to solve the determinant, but in this case I will use the rule of Saros. For this rule we will first have to rewrite our first and the second column. Then the rule of Saros says that the value of the determinant that contains 3 columns is equal to the sum of the products along the down-right diagonals minus the sum of the products along the up-right diagonals. So we are going to apply this rule. First we are going to add all the products of the down-right diagonal. So that is 0 times 0 times 1, which is equal to 0, plus 8 times 1 times 8, which is equal to 64, and 1 times 4 times 2, which is equal to 8. Now we are going to subtract this from the sum of the products of the upright diagonals. In this case that is 8 times 0 times 1, which is equal to 0, plus 2 times 1 times 0, which is equal to 0, and plus 1 times 4 times 8, which is equal to 32. Now, of course, we will simplify this to get the following, and that means that the area is equal to 40 over 2, and again we get that the area of our red triangle is equal to 20 squared units, and that is again our solution. Alright, now let's do the final method, the method number 5 of using triangle similarity. For this method, we will first going to mark some points. Let us label the bottom left corner of our big yellow square as D. Then we will label these two intersection points as E and F. Now first, let's notice this purple right triangle ADB. This triangle will have the height of 8 and the base of 4. Now let's also notice this pink right triangle AEF. This triangle will have the height of 6. Now, since EF is parallel to the line DB, that means that those two triangles have the same angles, which means that they are similar. We can use the rule of similarity and say that the relation between their heights AD and AE must be equal to the relation between their bases DB and EF. If we substitute our values, we will get the following. We can now cross-multiply this to get that A times EF is equal to 4 times 6, which means that A times EF is equal to 24. That means that the length of the line EF must be equal to 3. Now we can use this to find the length of this value FC, since it is equal to the difference between the length of our big yellow square with a side of 8 and the length of the line EF, which is equal to 3. So that means that the length of the line FC must be equal to 5. Now we can clear our image a little bit and save only these three values. We will divide our red triangle into two triangles, the green triangle on the top and the blue triangle on the bottom. So we can say that the area of our red triangle is actually equal to the sum of the areas of our green triangle, which has the base of 5 and the height of 6, and the area of our blue triangle, which has the base of 5 and the height of 2. Now we can translate this diagram into the following formula. From here, it is easy for us to find the area of the green and the blue triangles, because the area of the triangle is equal to the product of the base and the height divided with 2. So if we substitute our values in, we will get the following. Now we can simplify this to get that red area is equal to 15 plus 5, and we will get that the area of our red triangle is again equal to 20 squared units, and again we have our solution. Well, I hope you guys enjoyed this video. If you did, leave a like, and if you found another way to solve this problem, please write it down in a comment section so everybody can see. And of course, if you already haven't, subscribe to the channel for more content to come. And again, as always, until next time, see you guys and take care.